Okay, so the first thing that you're always going to start with is your given information. So we know that BC and CD are equal, and we know that AB and DE are equal. So this was the given information. And it's often useful to label this on your diagram as well. So if you know that BC is equal to CD, and AB, I'll use a different color for that, is equal to DE. Okay, so once you identify your givens, the next step in as far as being consistent with the approach that I would encourage you to use is interpret your givens. And so if the givens are statements, so if it says it's a midpoint or says they're supplementary or some phrasing in a sentence form, translate that into an equation or relationship. Okay, in this case, there's not, so you can move to the next step, which would be to introduce the elements of your end state. Okay, so our end state is AC. We don't have AC or CE in our proof anywhere yet. So if we look at those, though, if we look at AC and we look at CE, we see that those can each be expressed in terms of what's already there. And so that would be the next thing to think about. We want to introduce these elements, so AC and CE. My suggestion is to always introduce them in terms of either the form of the end state or usually just in the state themselves. So if you want to introduce AC, isolate that expression or that portion. So AC is a whole that's made up of two parts. So we can express that. The sum of the parts is equal to the whole. So AC is equal to the parts AB plus BC. And what's that an example of? Addition. What kind of addition? Segment addition, good. Okay, so by segment addition, we can introduce AC. At the same time, we can introduce CE using the same idea. It's made up of the parts CD and DE. And that's also segment addition. So we can include these in the same step too. You don't need two different steps for that. You can just leave them in that order. Okay, or both in step 2. And now, once you've introduced all of your end state elements, which I just did, now you have to kind of work backwards and see how can you work backwards to show that AC and CE are equal. Well, you can do one of two things in this case. One, you can either create a relationship where the sum of the parts of AC are equal to the sum of the parts of CE, or you can try to translate or transfer the elements of CE into the same elements that make up AC. So can we recreate or transform CE into AB plus BC? So those are the two options. So let's take a look at each one. So I'm going to do each one here separately. And let's start with the one where we transform CE into an expression that's identical to AC. Okay, if that's the way you approach it, you're going to take this equation from the second part of statement 2, and we're going to say CE is equal to, and then we're going to replace CD with its equivalent. Well, what is CD equivalent to? BC, so we're going to replace that with BC. And then we're going to replace DE with its equivalent to AB. Okay, so in looking at that, anytime you replace something, just strictly replace it, that's called substitution. Okay, and again, people have asked the difference between the substitution only and transitive property or substitution is this is a case of substitution only. We're only replacing values. Okay, but now by doing that, what we were able to do is now we create this expression, the sum of BC and AB, that we already have somewhere else in our proof, the sum of BC and AB. So here what we have is two things that are equal to the same thing. And we know if two things, CE and AC, are equal to the same thing, the sum of the parts AB and BC, then they're equal to each other. So we can make the statement that AC and CE are equal. And the justification is two things equal to the same thing or equal to each other is transitive property. Okay, and now again, anytime you use transitive property, it could also be substitution. We could have thought of this as taking this equation from step 2, AC is equal to, and then replacing this sum of terms with its equivalent, CE. So either transitive property or substitution works there. Bridget's question? Yes, you could have done either of those, yeah. Okay, now let's take a look at a second possible method of working through this proof. Okay, a different set of steps 3 and 4. Okay, so if instead of looking to go this direction where you're transforming CE into the same statement as AC, what we could have done is we could have just tried to create the sum of parts equal to each other. And the way that we would do that is we would take the equation from statement 1. So we would start with the equation AB is equal to DE. So all I'm doing here is I'm rewriting the statement from step 1. And now to get it into this form, I need to add BC to this side. And if I add a value to one side of the equation, I need to balance it out by adding either the same value or its equivalent to the other side. So what's the equivalent to BC? So I can add CD to the other side. Okay, if I did this, that's an example of addition property. If equals are added to equals, then the wholes are equal. Okay, so I could have used that relationship, which would then let me say this whole expression here, AB plus BC, is equivalent to AC, DE plus CD is equivalent to CE. And so what I could then do is finish my proof by replacing this expression with AC, this expression with CE. And so by, again, just replacing is the process of substitution. So by simple substitution, I would be able to get my statement as well.